Hello, this is the Math 136 Test 2 review. So show all work in order to receive full credit. So that applies to the actual test itself. There are some questions where if you just provide answers and do not back it up with work, you will not get full credit for the question. So make sure to back up your claims by either using what the problem is calling for, algebraic work, graphs, sentences explaining your reasoning, etc. Okay. Uh, do not change fractions to decimal. So if you have an answer and you have the simplified fraction, that's good enough. Don't turn it into a decimal. And we prefer exact answers. So in some cases, when you convert a fraction to a decimal, you'd have to write down some sort of approximate form. We don't want that. We want the exact answer. So if given a choice, uh, write your answer as a simplified fraction, so lowest terms. And same thing with radicals, make sure you simplify your radicals as well. And then as far as rounding goes, don't round unless we tell you to round to so many decimal places. Okay. So determine whether the relation represents a function. If it is a function, state the domain and range. The trick with this is I'm just looking at all of the x values with this set of points, and I'm looking for repeats, and I don't see any repeats on the x values, so it is a function. And what that means is each one of these inputs has only one output because these are the only ones that were shown. So if we had another question where maybe, or another version of this where we saw like -4, 5 along with the -4, 20, then it would not be a function because that input -4 has two different outputs, not a function. Functions have to have just one output per input. Now, repeated outputs are fine. So the domain is the set of all of the x values. And we've already determined that there's no repeats. Okay. The range is the set of all of the possible y values. So now the y values are 20, and you don't have to put them in order. That's fine. So 20, 13, 4. Now here's something funny. So -3 had an output of 13. 3 had an output of 13. That's fine. But we're only going to write the 13 once, so we don't need to write it again. And in fact, we shouldn't write it again because then that set would not be simplified. So then the last possible output for this function, if I can find where my pen is 29. So just the list of all the possible y values. Don't list the same one more than once, okay? If you put them in order, that's fine too. You don't need to. Okay. Find the domain of the function. So where is this misbehaved? Since it's a square root, it's going to misbehave wherever what's inside of it is equal to 0, or I'm sorry, is less than 0. So we can go directly to the allowable values by saying, well, what is allowed? Something that's either positive or 0 can go into a square root. So I take uh, the radicand and I set it greater than or equal to 0. The solutions to this inequality will be the domain of that function, since it's just a square root function. I can subtract 23 from each side. So I get -x is greater than or equal to -23. Then I can either multiply or divide each side by -1, or I can just negate each side, however you want to think about that. As soon as I do that with an inequality, I have to flip the direction of the inequality. So then I have x is less than or equal to 23. Now, here's the other, it's not really a trick, but it's an alternative approach. And I'm going to try and avoid giving you guys too many alternatives for these, but this one can really help people get their head around this whole, why do we flip the sign? So at this point, when we get it to here, what we can do, instead of doing that multiplication, we can add the x to both sides. So then we have 0 is greater than or equal to negative 23 plus x. And then we can add the 23 to both sides. So then we have 23 is greater than or equal to x. And then we can rewrite this in the reverse direction. So then if 23 is greater than or equal to x, then that means that x is less than or equal to 23. And you can see we get the same answer. In interval notation, this answer is going to be negative infinity up to 23 inclusive. Okay. And I can just put that right up here. And so we're not solving an equation, we're finding a domain. You can do a quick sanity check with this by just taking any number that you see in there and just tossing it in, making sure it works. So, right, so let's try, so from negative infinity up to 23, zero's in there. I toss that in, I get the square root of 23 minus 0, which simplifies to the square root of 23, which works. Now, if I tried something like 24, 23 minus 24 is negative 1, then I'd have the square root of negative 1, which isn't real, and we're looking for a real output. So anything that generates a non-real output, we're going to want to throw out, which is why this works. Okay, so then there's our domain again. And then make sure you put it up there. So I know which one you want. Alternatively, if you put a box around it, that's fine. Now, if you write something different in the box and then you put something else up there, you're like trying to give me two answers, then if one of them's right, then that's great, but it's not one of those things where, I'll pick the one that's right and then give you full points. If you state two answers like that, I got to take away points. So make sure that if you're copying that down up there, you copy it down correctly. So I know you're not trying to trick me or something. Okay, find and simplify the difference quotient for the function. So my difference quotient is f of x plus h minus f of x over h, secretly just slope. And then the x squared plus 5x plus 3. So I'm going to just leave some space in there. So I have x, so blank squared plus 5 times blank plus 3, and then minus blank over h. So what I'm dropping in here is x plus h and x plus h. And then what I'm dropping in over here is just the original function. So x squared plus 5x plus 3. So this is the f of x plus h. This, you can see, is the original function. Now, your goal with any one of these problems is to cancel the h in the denominator. So when it says find and simplify the difference quotient. So this thing that I wrote down here, this whole thing, I found it. I found the difference quotient. It's not simplified yet, though. That's the hard part. So if you can set up the difference quotient, that is half of the points right there. Okay, you found it, but then simplifying it, that's the rest of the points. So now x plus h squared, multiply that out. So I get x squared plus 2hx plus h squared. It's a perfect square trinomial. Distribute the 5, so I have 5x plus 5h. Okay, 3 is just there. Distribute the negative sign, so I have minus x squared minus 5x minus 3. Okay, and that's all over h. And then something nice happens. So this x squared cancels this one. This minus 5x cancels this 5x, and the minus 3 cancels there. So now I'm left with 2hx plus h squared plus 5h all over h. And now I just kind of feel set up for success because I see everything that's left has an h as a factor. So let's factor that out. So I have h times the quantity of 2x plus h plus 5 after I've factored it out. And now I have hit my goal, which was to cancel that h on the bottom. And I have found and simplified the difference quotient. So my final answer is 2x plus h plus 5. Okay. For the given functions f and g, find the requested function and state its domain. So f over g. So f over g of x, that's going to be f of x over g of x. And then you substitute in what those functions are. So 4x plus 3 over 2x minus 5. Now, if I factor these, so if I factor like a 4 out of the top and a 2 out of the bottom, I'm not going to get anything other than fractions over here. I'm not going to get anything that cancels down. So this is it. That's it. That's the function. So that's the first part of the answer. So f over g of x is 4x plus 3 over 2x minus 5. Nothing else tricky happens with that. But don't forget, there's two parts to this. So we found the requested function, so we've hit that. The domain. So this thing right here needs to be taken into consideration. So we need to figure out where that is equal to 0 because we don't want to divide by 0. So then we can add 5 to both sides, divide both sides by 2, and we get 5 halves. So then my domain is x is any number such that x is not equal to 5 halves. And when in doubt, use interval notation. Like I want to say I have that in the instructions somewhere, but I don't know if it's on this one. But when in doubt, use interval notation. If the question is not directly calling for a particular variety of notation, then as long as it's correct, I'll accept it if I'm not asking for a specific one. But that's me. Okay, so pay attention to your particular instructor. So my domain is negative infinity to 5/2 union with 5/2 to infinity. So all of the real numbers except for 5/2 is what that's saying, because I'm not being inclusive on the 5/2. Okay, determine whether the graph is that of a function. If it is, use the graph to find its domain and range, the intercepts, if any, and any symmetry with respect to the x-axis, y-axis, and or origin. So I'm looking at that, and I can see that if I let's try and make a straight line here. So I'm passing lines through it. So pretend they're vertical lines, and it's not hitting the function in more than one place. So it is a function by vertical line test. So VLT. And then if it is, use its graph to find the domain and range. So the domain of this, so I can see that it's a quadratic function, and we know the domain of a quadratic function is all real numbers. The range of a quadratic function, well, we have to pay a little bit more attention. So we can see that the vertex, if we look really closely, the vertex is at -1, 4. Don't be tricked by that 5 right there. Count the notches, 1, 2, 3, 4. That y value is 4 there. So, and it doesn't go above 4. 4 is the highest value. It's the absolute maximum for this function. So that my range is going to be -infinity up to and including 4. So I need to make sure I use a square bracket, because that 4 is actually on the function. That's the highest y value the function has. Let's see, intercepts. So let me mark those in a different color. So I have an intercept at 0, 3, and I have another intercept at 1, 0, and there's another one at -3, 0. And if it just says intercepts, you're just tossing all of them, the y-intercept and the x-intercepts, you're just tossing them all in as ordered pairs. Don't list them as values, because then I don't know if you mean the x-intercept as the y-intercept. So if it says intercepts, you can do that, or you can, if you want to list the y-intercept separately and then the x-intercept separately, you can do that too. I'll forgive you. I won't be mad. Okay, any symmetry with respect to the x-axis, y-axis, and or the origin. Well, if we just moved it one to the right, we'd be good for y-axis symmetry. But since it's not symmetric with respect to the y-axis, and then if it had the x-axis symmetry is a trick. So that's a trap. So if you just said it was a function, but then you said it was an x-axis symmetry, you have created a paradox. Okay. So your only possible answers for symmetry for a function that you have declared is either y-axis or the origin. It does not have y-axis, because if I fold that along the y-axis, it doesn't overlap itself. It doesn't have origin symmetry, because if I rotate that thing around 180 degrees, it is not going to look like itself again. So no symmetry. And you have to say no symmetry or neither. Or so there's your, you can either say, so no symmetry, neither, whatever, none. So, one of those. No symmetry is great there. That just makes sense. Okay. Given the function f of x equals x squared minus 7 over x plus 2, if x is equal to 1, what is f of x? What point is on the graph of f? So if x is equal to 1, then we have f of x is equal to f of 1. So then we have 1 squared minus 7 over 1 plus 2. Now, if that bothers you, you can always just set it up like I mentioned in class, where you have these blanks, and then into those blanks, you drop in the 1 like that. That's perfectly fine. So 1 minus 7 over 3. So now I have negative 6 over 3. So that's negative 2. So we can see that f of 1 is equal to negative 2. And then the point on the function is 1, negative 2. So those are the two answers for this one. So f of 1 equals negative 2. So then remember, the input is x, the output is y. So then for the ordered pair, you take that input, comma, output. Given function f of x equals x squared plus 3 over x plus 5, list the y-intercept, if there is one, of the graph of f. This is like the easiest one on there. So y-intercept, you just do f of 0. So I have 0 squared plus 3 over 0 plus 5. So that's 3/5. So, and that corresponds to the point 0 3/5. And if it's just asking for the y-intercept and you state 3/5 there, that's fine. Okay. Determine algebraically whether the function is even, odd, or neither. I want to see algebra here. I want to see you substituting in negative x in place of x and doing the correct algebra to show which one of these possibilities it is. Don't just guess and hope you get full points for your guess, because you will not. Okay, so I have dropped in a negative x in place of x everywhere. And the first thing I need to do is simplify. So the top simplifies to x cubed, because negative x cubed will be, so just some side work. If I have negative x cubed like that, remember that's negative x times negative x times negative x. So I have an odd number of negative signs, which means I'll have a negative result. So now, I guess, oops, oh no. Let me baby step through that just a little bit more for you. So this is going to be negative x cubed. This is not the same as this. Notice where the cube is, and I just backed that up over here. Okay, so this is just side work if it's still bothering you. The negative x squared, that's negative x times negative x. So that's an even number of negative signs. So that just simplifies to x squared. So now I have 6x squared minus 2 in the denominator. And then up top, negative x cubed makes a positive x cubed. And then we can see we have, after simplifying, x cubed over 6x squared minus 2. It looks very similar, but it's missing a negative sign. So we'll say that we have to say that it's not equal to the original function. So far, we can declare that it's not even, but we're not done because it asked even, odd, or neither. So the next thing to check is to see if it's odd. To check if it's odd, I factor out a negative sign, or I rewrite it as negative parentheses negative itself, which is the same thing as just factoring out a negative sign if there isn't a negative sign there already. And now I look at it and well, that negative sign out front, that's fine. This is still, if I you know what, let me go downward instead of, oh no. Okay, it jumped all the way down, or all the way up there. Okay. So I just wanted to go down. So you can, so if that negative is out front, it will commute up to the numerator. We can back that up with work if we want, or we can just say, I have taken enough of the required prerequisites that I see what he did there. And now I have a negative, and then in parentheses, we can see that that's the original function. So this is equal to negative f of x, therefore it's odd. So then my final answer is odd, but again, I'm grading your work as well. Okay. Use the graph to find the intervals on which it's increasing, decreasing, or constant. So increasing is from here to here. Okay, I had a bit of an interruption. So we're looking at number 9. Use the graph to find the intervals on which it is increasing, decreasing, or constant. Now, increasing, it's doing that. Decreasing, it's doing that. Constant, it is staying the same. Well, let me see if I can make it perfectly horizontal. Does that look horizontal? Or is that askew? I can't tell. All right, so now there's more formal definitions for this, right? So increasing, as x increases, y increases. So okay, so as x gets bigger, y gets bigger. Decreasing is as x increases, y is getting smaller. It's decreasing. And then as x increases, y stays the same. That's not, like basically it's, you don't have to say as x increases. You could say for any x in some interval, if it has the same y value as all the other ones, then it's constant. Okay, so increasing. So this portion of the graph, so from here to here, we can see it's as x is getting bigger, y is getting bigger. Okay, and then the way that we describe that as an interval, the intervals in question are going to be x intervals. So for increasing, we're going from negative pi over 2 to positive pi over 2. So we're looking at the x values only. The y values are showing us that it's increasing, decreasing, or constant, but when we're reporting on these, then we want to just describe the x values where these are happening. Okay, and then from negative pi to pi over 2, so we can see from here to here. So negative pi to pi over 2. I'm sorry, to negative pi over 2. And then you use a comma to separate these results. You're not going to use a union symbol. And then we're also decreasing from pi over 2 to pi. Okay. Constant. There are none. So we say none. Okay, and then that's it. These are the results. There you go. Number 10. Find, so the graph of a function f is given. Use the graph to answer the question. Find the numbers, if any, at which f has a local minimum. What are the local minima? So I can see that this guy right here is the only one that qualifies as a local minimum. And so you can see that it's this point 0, -2. So the number at which it has, so has local minimum at x equals 0. But what are the local minimum? So local min is y equals -2. So now just to kind of put that all together, so there's a local min, so local minimum of y equals -2 located at x equals 0, or you could phrase that backwards. So located at x equals 0, there is a local minimum of y equals -2. So the y value is uh, the local min or max. The x value is the location of the local min max, or max, so min or max. Okay. Okay. For the graph of function y equals f of x, find the absolute maximum and the absolute minimum if it exists. So this almost looks like it's a closed interval, but we do see this one open circle there, which means that it's not closed. So it's got one opening there. And we can, if we kind of just rank the values that we can see that there is a highest y value. So right there, that's an absolute max. Okay. So our absolute max of y equals 6 at x equals 3. Now, the lowest y value that we can see is 1, but it's not on the function. So lowest point is not included. So it's not actually on the function. We can get close, but y will not get to 1. So what that means is we can get to 1.1, we can get to 1.01, we can get to 1.001. So we can get closer and closer to 1, but we can never reach it. There is no minimum value, so there's no absolute minimum. So because if you give me a number, like we can just play this all day where we get closer and closer to 1 without ever getting there, but there's no, like we know 1's at the bottom, but we can never get to 1. Okay, and then there's some fancier math around that too. But don't worry too much about it. You don't have to write a paragraph or give an explanation. You can just say there's a hole there where I want an absolute minimum to be, and we can just state that there's no absolute minimum. Okay. What I'm trying to do is help build your intuition about it to try and make it make sense if I can. Number 12. Find the average rate of change for the function between the given values. Oh, so these are x values, just so you know. And the average rate of change you can write that as delta y over delta x. And we have this formula. But remember, it's really just the slope formula, except with function notation in it, because what we're doing is we're talking about points that are on the function. So it's the same formula. So now we can say that A is 1 and B is 5. So then we have f of 5 minus f of 1 over 5 minus 1. Okay, well, you can plug it all in at once. For this one, I don't see them asking for us to do a secant line for this one. So we can just play them where they lie. So f of 5 is going to be 2 times 5 minus 1 inside of a square root minus f of 1. So that's going to be square root of 2 times 1 minus 1. And then that's all over 4. So then that's the square root of 9. So that's going to be 3 minus 1 over 4. So I get 2 over 4, which is 1/2. I'm happy if you just put a 1/2 up there. Okay. Find the equation of the secant line containing 1 comma f1 and 2 comma f2. Here it's maybe a little bit more useful to compute these guys ahead of time. So I have 1 minus 2 is -1. Yeah. I'm writing it this way for those of you who are not as comfortable with the function notation yet. So I end up with 4 minus 4 is 0. Okay, so now I have these points. And now that I have these points, find the equation of the secant line. All this turns into now is just an old-fashioned, here's your slope formula, but really what we're supposed to be thinking about is that the slope of the secant line is the average rate of change between 2 points on the function, this f of b minus f of a over b minus a. But again, I keep telling you guys, it's the same formula. And then we're just going to go ahead and use the slope intercept. I'm sorry, not the slope intercept formula. We're going to use the point slope formula and then turn it into the slope intercept. So we're going to use this guy here. All right, well, let's do this stuff. So this is f of 2 minus f of 1 over 2 minus 1. So this is 0 minus -1 over 1. And so that's 1 over 1. So that's 1. So there's the slope of our secant line. And then you can choose either one of those points. The one that I noticed that gives me the least amount of work is 2, 0, because I can do y minus 0 equals 1 times x minus 2. So then I end up with y equals x minus 2. And the equation of the line is what we're looking for. So that's it. Okay, graph the function. Let's see. So what you want to do with this, you want to figure out what's happening at important places on this piecewise function. One important place we can see is that every piece seems to connect up at 2. So what I first want to do is find f of 2. And if x is equal to 2, then the output of the function is -8. Okay, that looks important. I see one more boundary at -7, so let's go ahead and find f of -7. So that's in the first piece, so then that's going to be -7 plus 4, which gives me -3. Okay. Other important considerations, so y-intercept. So that's f of 0. So f of 0, we look for the piece that has 0 in it, so that's the first piece, so that's going to be 0 plus 4, so I get 4. So far I have these points that are actually on the function. 2, -8, -7, -3, and 0, 4. We can look for x-intercepts. We have to be careful and make sure that any solutions we find actually live in the corresponding piece where we found them. With a piecewise function, you're still setting f of x equal to 0, but what you're doing is setting each individual piece equal to 0. So you have to set x plus 4 equal to 0. Technically, you have to set the -8 equal to 0. You can skip it if you're like, that is silly, because it is. And then, of course, we get x equals -4. Here, that doesn't make sense, so we just skip it because it's just automatically a false statement. And then for the last one, we get x equals -4. I'm sorry, +4. Now, this first one came from the first piece, so we got -4. Is -4 between -7 and 2? Yes, it is. So this one's okay. Is +4, so that's in the last piece. So is it greater than +2? Yeah, it is. So both of these are acceptable. So we have the x-intercepts -4, 0 and 4, 0. Be careful because it is possible that you could get a solution that's not actually in the domain of that piece. So what we've done is we found points that are on, these are all points that are on the function, okay? X-intercepts you have to be careful with. And then the kind of the holes or the open circles. Let's just, I'm gonna put a question mark because sometimes pieces join up. That's allowed. So as x is going to 2 from the left, what's f of x doing? So when I say from the left, I mean from the negative direction, but like on the number line from the left of 2. So we have when x is 2, it's the second piece, but right before that on the left, it's in the first piece and it's getting closer and closer to 2, and then it's doing whatever it does when it gets to 2. But as it gets closer to 2, what's it doing? It's going to look like 2 plus 4. And all I'm doing is I'm plugging the 2 into the first piece to just see what happens. So we can see it's going to 6. So we have an open circle at 2, 6. And then from the other direction, from the positive direction, from the right, as it's going to 2, it's looking like -x plus 4. And as we come from the positive direction and get closer to 2, the function is in that third piece. So it looks like it's heading towards -2 plus 4 is equal to 2. And all I'm doing is I'm plugging the 2 in for x in that third piece to figure that out. So we have another open circle at 2, 2. So next, let's go ahead and plot what we have. And uh, the first and the third piece are just linear functions. So this piecewise function is not going to be too difficult to graph. But let's plot the points we know. So 2, -8. Right about there. -7, -3. Right about there. 0, 4. Okay, what else do we know for sure? we have negative 4, 0, and 4, 0. And then our open circles, we have 2, 6, and 2, 2. Okay. And that's about all we need. So our first piece, looks something like that. So we're starting here at negative 7, negative 3, and it's just a linear function until x gets to 2, and then what it's doing is it's jumping down to this point down here, and then it's just going to end up being an isolated point. And then it jumps back up to here, to this open circle, and it's just going to look like a linear function going down that way forever. We can make that line just a little bit better. All right, it's deciding not to straighten it out for me, so we'll just live with it. And it might be nice, and it might be in your best interest to go ahead and label those important points that you worked so hard to figure out. I totally just wrote on top of that 5. Oh well. That hole's not actually on the function, but we're going to label it anyways. Same with that one. And then we have 4, 0. And then this guy all by himself, all the way down there. All right. Well, I would say we just graphed the heck out of that piecewise function. All right, on to the next one. Graph the function by starting with the graph of the basic function and then using the techniques of shifting, compressing, stretching, and or reflecting. Okay, so let's take a look. We have f of x equals x plus 6 quantity squared plus 6. So that's telling us left by 6. This is telling us up by 6. And make sure you know how to describe those in words. You are expected to know how to do that. And, you know, as long as you have enough description in there, it's fine. So our parent function is y equals x squared, right? So that's the square function. And then we're going to do so this is the shift left by 6. And then we're going to do, for our last one, the shift up by 6. Okay, let's zoom in and take care of it. If I can find my pointer here. Sometimes I control. Well, sometimes the computer even cooperates with me. Okay, so there's our parent function. So this is the y equals x squared. And then 6 to the left, all that's happening is we're moving each point 1, 2, 3, 4, 5, 6 places to the left. There's our new, or at least our second one. Okay, and then last, so this is y equals x plus 6 squared. And then we're shifting each one of those up 6 places. All right, and there's our final picture. So this is what we wanted, f of x. And I'll just make it a little bit thicker, especially if I'm, if I was doing this all in one color, I'd want to make that one stand out a bit. So I know that's the one I wanted, and I'm also labeling it with f of x, so I know for sure that's the one I want. All right, there we go. Next, write an equation that results in the desired transformation. We have y equals x squared, and it says vertically stretched by a factor of 4. So if it's being vertically stretched, that's when we just multiply the outside. And that's it. So it's just 4x squared. Okay, find the function. Find the function that is finely graphed after the following transformations are applied to the graph y equals square root of x. The graph is shifted down 5 units, reflected about the y-axis, and then finally shifted right 2 units. So we have the square root function. Y equals square root of x. And then it says shifted down 5. So then we'll have y equals the square root of x. And then minus 5, and that minus 5 is outside of the square root. And then it says reflected about the y-axis. So to do a y-axis reflection, you flip the sign on the x inside. And then finally shift it to the right by 2 units. So as it is, I want to shift it to the right by 2 units. So inside of the square root, so I keep my -2, I'm sorry, my -x, and then I add, I'm sorry, so this one's a little bit weird. To shift it to the right as it is, I'm actually going to add 2. I know it's weird. So how do we justify that? How do we make that make sense? Because this is it. This is the final answer, but I'm not going to just stop there and move on. I'm going to give you just a little bit more explanation once I write it down, or once it lets me. Okay. Experiencing terrible lag today on my laptop. -5. Okay. Something simple. Just trying to write that down. So what happened? Because I have the -x there, the way that you can think of that is from the previous step where we did the reflection. You can think of that x as kind of being in parentheses. And if we do x -2, then if we distribute that negative sign, then it turns into a +2. And if you've done a bunch of these, then you just kind of automatically know it should be a +2 sometimes. So uh, what what can help a lot with this is if you just check values or do quick sketches of what it should look like. And sometimes to do that quick sketch, you need to just modify it a little bit algebraically. Okay, well, I guess that's not technically equal. Okay, okay, let's move along. Graph the function by starting with the graph of y equals x squared and use transformations, shifting, compressing, stretching, and or reflection. Well, they didn't give us something starting out that looked like what it was supposed to look. I can't use those things until I have this written in the vertex form. So to get this to vertex form, I just do completing the square. So I'm going to factor off a negative from the x squared and the 6x and rewrite that as negative quantity x squared minus 6x. And I'm going to leave some room. And then the -7 is just out there for the moment. So I'm going to take that -6 times a half, and I get my magic number. Magic. Then I'm going to take my magic number and I'm going to square it, and I get 9. This completes the square. So now that I know what completes the square, I'm going to add it and subtract it immediately. So that's effectively just adding 0. It's not changing anything. So now I'm going to factor just this part. So I have negative quantity, and I'm going to make another parentheses, and I'm going to factor this x squared minus 6x plus 9, and that factors to, look at your magic number, so x minus 3 quantity squared, and then this 9 just comes on down, just like that. And then, oh, hey, that -7's still there. Next, I'm going to distribute the negative sign through the parentheses. So I have negative, and I'm going to leave the x minus 3 squared as is, because that was my goal, to get that x only written in one place. And then a -9 makes a +9. And then one more step to simplify everything. So I have negative x minus 3 quantity squared plus 2. Now I can do all of that fun function transformation stuff. So that's an x-axis reflection. That's shift right 3. That's a shift up by 2. So, and our parent function is just y equals x squared. So this guy again. Okay, and I want to do my shift to the right by 3 first. Okay, so there's my next iteration. Then I need to reflect about the x-axis. Oops. And finally, I'm going to shift everything up by 2, and that's going to be my last transformation. And as long as you're capturing the general behavior, that's what I'm most interested in. Just be careful. Don't be extra sloppy or something. Okay. I gotta be able to read it. I gotta be able to see it. So something like this is good. Hey, 19. Find the vertex and axis of symmetry of the graph of the function. We don't have to find the graph. We just have to find the vertex and axis of symmetry. So we can use that formula -b over 2a. So so our b is 10, 2, and then our a is -5. So that is -10 over -10. So we get 1. Okay. So that's the x component of the vertex. And then to get the y component, we just plug that value into the function. So we have -5 times 1 squared plus 10 times 1 plus 7. So that's -5 plus 10 plus 7. So we have 12. So my vertex is 1, 12. My axis of symmetry is x equals 1. Graph the function using its vertex, axis of symmetry, and intercepts. Okay, so -b over 2a is going to be -2 over 2 times 1. So we get -1. To get the y component, we do f of -1. So we have -1 squared plus 2 times -1 minus 3. So we have 1 minus 2 minus 3. So we have -4. So my vertex is -1, -4. Axis of symmetry is x equals -1. It's just the x component of the vertex. Okay, and then for the intercepts, for the y-intercept, we just look for f of 0, and we see that's -3. So we have 0, -3. For the x-intercepts, we set f of x equal to 0. So we have x squared plus 2x minus 3 equals 0. So we have x plus 3 times x minus 1 is equal to 0. So then that is x equals -3 and x equals 1. So we have -3, 0 and 1, 0. So now our intercepts are, let's see, 0, -3, -3, 0, and 1, 0. Okay, so there's all that important information. Let's go ahead and plot some points. So -1, -4, 0, -3, 1, 0, and -3, 0. Now our axis of symmetry is x equals -1. So going through here, and you can reflect your y-intercept across that. Okay, and then there's our sketch. I've definitely drawn better. Okay, good enough. I don't know why that's a double arrow. All right, I'm happy with that. So the pattern I'm hoping you guys are noticing is that you can figure out a little bit by analyzing the function and get at a picture of it without having to make a whole table of values. The table of values is still there if you need to make it, but you might have shortcuts. That's the whole idea. We're giving you more shortcuts. Determine without graphing whether the given quadratic function has a maximum value or a minimum value, and then find that value. So we can see that the a is equal to 1, which is greater than 0. That's positive. This means that it is concave up. So it opens upward. So in other words, it looks like this. So if it's opening up, then it has an absolute minimum. Okay, so there's our first answer. Okay, what is that absolute minimum? Well, it's going to be at the vertex. So let me just take out that nice little vertex formula, or if you wanted to, you could complete the square and get it the function into vertex form. That would also do the trick for you. But I think that most of you like the formula better. So we'll just do it with the formula. So my b is 2, my a is 1, so I have negative 2 over 2 times 1. So I get negative 1. And then I just plug that into the function. So I have negative 1 squared plus 2 times negative 1 minus 8. So I have 1 minus 2 minus 8. So that's going to be negative 9. So my vertex is at negative 1, negative 9. So then I have an absolute min of y equals negative 9 at x equals negative 1. Okay. Use the figure to solve the inequality, and it's saying f of x is less than 0. So it's not including the x-axis, but I can see that the function is less than 0 along here. And then the values of x are the solution to this. So from here to here. So then my answer is that f of x is less than 0 when x is between negative 5 and 3, not inclusive. Okay. Solve the inequality. F of x is less than g of x. So you have to look at the picture and figure out which one's f of x and which one's g of x. So g of x is the straight line, and then f of x is the parabola. So we can see that the parabola is above the straight line for these parts here. And it's just greater than, so we're not including these, but those points are important. So we have, it's going to be from negative infinity up to negative 1, and then it's going to go from 2 to infinity. So we have this negative infinity up to negative 1, and then here we see it's 2 to infinity, because they already gave us where the functions are intersecting. So then my final answer is going to be negative infinity up to negative 1 union with 2 to infinity. The common mistake with these is you use y values by mistake when you're doing this. Do not use y values. So the solutions to these. Okay, I don't know what. Apologies for all the technology. The solutions to these inequality problems will be values of x. And in particular, they'll be x intervals. Okay. All right. Almost done. Solve the inequality. Well, you can solve these by graphing. You can use the my favorite option, which is what I'm about to do, because I'll get done faster. So I want to solve x squared minus 3x minus 10 equals, or I'm sorry, is less than or equal to 0. So I'm going to think of this as f of x, and I'm just going to figure out when this is 0. So if we were graphing it, it's the same thing as if, just finding the x-intercepts. And I'm looking at that. So -5 and +2 will do that for me. So I get x equals 5 and x equals -2. Then I make a number line. And I mark off -2 and I mark off 5. And I just need to do one test value. And I use 0 a lot. But it doesn't have to be 0. And then another thing that you want to do if you're going to be marking test values in here. So notice that it's a non-strict, or it's not a strict inequality, which means that we're including the points on the x-axis. So I'm going to use closed circles. So I'm going to do something different. I'll pick instead of 0, I'll pick 1. But you could pick 6 or you could pick -3. So what we want to do is check each region. But since it's a quadratic, once you know one region, it alternates. So you just figure out what the next regions will flip to since it's alternating. So I'm going to test f of 1. So I get 1 minus 3 minus 10. So I get -12. We can see that's negative. So this region's a negative region. And what that means is that these other two regions will be positive. And what we were trying to find was less than or equal to 0. So then the region that we want is just this one. Now you could have more than one region, but for this problem, it's just this, and the solution is just -2 inclusive to 5 inclusive. That's it. We solved it. Okay, the next one. I have x squared plus 4x minus 21 is greater than 0. So you can think of f of x as x squared plus 4x minus 21. We want to set that equal to 0 and solve for x. So that looks like x plus 7 times x minus 3. Yep. And then that's x equals -7 and x equals 3 as solutions. Make my number line. So -7, +3. Check my inequality. It's not strict, so I'm going to write open circles here because I want to make sure I'm not including those. And I'm just going to use 0 as my test value. So test f of 0 If zero's on one of those boundaries, make sure that you just use a different value other than zero. Like I demonstrated, in any value in that region will tell you what the whole region's doing. So this is negative 21. So that's less than zero. So that's negative. So this is negative, which means these other regions are positive. Okay. And then what we wanted was greater than zero. So we want these positive ones. There we go. And in interval notation, that left region is negative infinity up to -7, not inclusive. So I use parentheses, union with 3 to infinity. Okay, not inclusive on the 3. And that's that. Like I said, if you want to sketch the function, you can, and it doesn't have to be a great sketch. But this is how you can do these with about the bare minimum of work to solve them. Now, what you cannot do with a quadratic inequality is try and just solve it like an equation. You can certainly try that, and really what you end up finding is just the places where the function would be hitting the x-axis, and then you have to use those to divide the x-axis up into regions. If you're not sure what to do with these, just graph them and look at where the function is above and below, and you'll know that uh, you know, what is dividing, or where it's changing from being above the x-axis or below the x-axis are those x-intercepts. Okay. All right. Good luck on test 2.